The Sporlan division of Parker Hannifin proudly sponsors the Advanced Refrigeration podcast. There are a lot of questions surrounding the transition to A2L refrigerants and a lot of talking heads disseminating nebulous answers. But when your technician is face-to-face with the first A2L transition project, where do you turn for real-world answers about this specific job? Parker Sporlan's Virtual Engineer is an innovative online design tool to size and select the correct components for climate control and refrigeration applications. Get your A2L system flow and component selection answers in 3 simple steps. Enter your application details, size, and select products, then download your project files. It's that easy. Try it at absolutely no cost. Visit sporlan.com and navigate to the Resource Center. Parker Sporlan, leading the charge.
Good evening, everybody. Welcome to Advanced Refrigeration Podcast. You're the host, Brett Wetzel, Kevin Gumpus, and we have a special guest from Zero Zone, Adam Selesky. How are we doing?
Good, Brett.
How is your guys' week? Usually I just ask Kevin, but I'm going to ask you too, because I know it's cold where you're at.
Similar probably Kevin's experience with the cold weather. We get a lot of calls and we get a lot of issues with cold, especially the gas cooler settings. That's been a little bit of reprieve this week because the weather has warmed up a little bit. But the first cold spell of the year, we seem to get hit pretty hard, all across the country. And this one was a good one because it was from West Coast all the way East Coast. A lot of tuning and a lot of fixing parameters that probably haven't been set up properly on startup for the cold weather.
You do a lot of startup with Zero Zone. So are you finding that we start these things up in the summertime and then things when the ambient hits, when it becomes different outside, then we essentially start having issues where there wasn't issues before?
Yeah, I think there's a lot of settings in these controllers now. And as we know, there's hundreds and hundreds of settings and it's easy to overlook things. And you don't really, unless you're really looking and you got to go through setting by setting, it's easy to overlook certain things. You've got the gas cooler, fan speed and control of the cycling of the fans, and you've got the high pressure valve and the flash gas, and they all have to work nicely and play nice in the sandbox per se. And if they don't, things can go awry pretty quickly and crash the system and have a lot of instability.
We're going to talk about gas coolers this week. I guess we got some stuff that we wanted to talk about with some of the heat reclaim stuff that you guys are doing, as well as some of the gas or bypass, since we know that you guys are deeply involved with a lot of that stuff. And then if we have enough time to talk about it, we can talk about what we talked about, Kevin, last week a little bit with the gas cooler control. I want to see what Adam is thinking, what he's seen that works. We have our opinion, see if he's on the same page as us, or if we're just pissing in the wind here with what we're thinking. You know what I mean? But if you want to start, do you want to bring up? So we're going to talk about the heat reclaim. I've been wanting to see this rack. Kevin's talked about it a whole bunch. So I'm just going to add it up to the screen. I wanted to see the actual P&ID so I can get an idea. Because like I said, Kevin's been describing it, but I haven't been able to actually get my hands on it. I'm going to bring it up the screen if you want to walk us through it.
Yep, absolutely. So just give me a little bit of background to the audience. This is a trench critical rack for a small grocery store, or not really grocery store, but a pharmacy. So there's a couple small loads on this, a typical small freezer box and a typical small walk-in lineup of cases. But this rack is special because it's not just doing the cooling for the refrigeration for the walk-in box, the cooler in the freezer, but it's also doing all the HVAC cooling in the summertime, and then it's actually utilizing heat reclaim to actually warm the building as well. This is attached to a geothermal unit, so we are producing chilled water to provide the HVAC cooling. The freezer and the coolers are direct expansion CO2. The HVAC cooling in the summer is accomplished by cooling glycol and then circulating the chilled glycol through the loop. And then we also have a secondary heating loop that in the winter time we utilize, and we produce hot glycol, then pushes through the air handling units to produce heat in the winter. Now, one of the challenges we have had and designed around on this rack is in the wintertime, how do we have enough heat? Because the design of this door required a lot of heat in the wintertime. And we know that during the wintertime, a lot of refrigeration load goes away. It may be running 25%, if not lower at part times. So it's very difficult then to get full design THR out of a rack if you don't have the refrigeration side then to produce a THR. So this rack is connected to a ground loop, which then we scavenge heat out of it and basically turn this into a heat pump in the wintertime. That warm water mixes with the chilled glycol, and the chilled water loop then produces an artificial load to ramp up the refrigeration and produce the heat we need. So that's a little bit of background story on this, and I'll walk through the P&ID. Brett, if you can zoom in a little bit on the...
That's going to be entirely on you.
Oh, it is? Okay.
You have total control of that, so you're just going to have to zoom it in via the PDF, unfortunately.
You got my screen update?
Yeah, we do. Got it. We're all good.
Perfect. Okay. So we've got two heat exchangers on this. The refrigeration side of this rack is pretty typical. It's not much different. It's a booster system. We've got a couple of low temp compressors and 4 medium temp compressors, typical booster rack configuration. Where we've got some unique characteristics of this rack is we've got 2 heating loops. This DHW heat exchanger 1 is actually just domestic water, but that is secondary to the glycol heat exchanger that we've got here. From a control sequence, our primary motive is to produce hot water. Then secondarily, if we do have something still to give, then we'll produce hot water for domestic use. The hot water load is pretty light. There's basically the public restroom is the only thing utilizing hot water. So it's a pretty light load, and all the majority of efforts and focus really goes on to this heat exchanger, which produces the hot glycol for the wintertime conditions. Both of these heat exchangers utilize a Danfoss CTR valve, a modulating stepper valve. So we are controlling this based off of the supply temperature. When we get a call for heating from the building control, we'll enable these circuits, and then we'll modulate these stepper valves to produce the supply water temperature. At first, we do not modify anything from the rack perspective. If we can produce the heat without artificially raising the head pressure or the gas cooler temperature, we try to do. So first stage basically is we modulate these valves. If in fact that we're not meeting the set point and this valve is 100%, then we'll start raising the gas cooler outlet temperature by reducing or raising the set point of the fans, the drop leg temperature, which reduces the fan, raises the drop leg temperature, and then artificially then with the high pressure expansion valve can raise the discharge pressure up to the valve. That enables us to produce more heat.
So that other CTR valve, is that a gas cooler bypass right there?
Yeah. So we have a third valve right here. This is, again, the same CTR valve that we're using right here. Typically, that only comes into play is if we can run in the situation where we're giving everything that we've got. It's really cold out. This store is located in Chicago, so we can easily see a sub-zero temperature. So if it's minus 20, let's say, we're trying to artificially raise the discharge pressure. Our fans are off. We're doing everything we can, and we've scavenged all the heat. We can get to some pretty cold temperatures coming out of the gas cooler because there's no heat left to give. In that situation, a last resort would be to bypass the gas cooler directly across the valve, and that produces a warmer temperature, which is being monitored by the high pressure expansion valve control, which then will take over control and then maintain head pressure properly. You may be wondering about this heat exchanger. I can get into this in a little bit. One unique quality, again, as I mentioned before, this does have a ground source thermal loop. which we're pumping. It's multiple wells drilled vertically down into the ground, which we can either dump heat in the summer or pull heat out of the ground in the wintertime. So this rack, what the intent is, this is just a desuperheater. It is an air-cooled gas cooler. It is not adiabatic, but the design around this is to basically desuperheat and bring the temperature down and basically dump the high-grade heat to ambient. And then any residual heat, then this becomes a subcooler. So we're using the ground source, the geoglycol loop, then to cool this further. So what's neat about this is it was 95 to 100 degrees this summer, and we were still running 70-degree condensing temperature. So very efficient. It allows the compressors never to even get close. I know people talk about an adiabatic condenser, about not running transcritical, but in all reality, they are running 85-degree gas cooler out, and essentially that is a transcritical. But in this situation, it was unique to walk in the rack room and just the compressors are just humming and so quiet and running at nearly a 70-degree condensing temperature because we've got this glycol that is providing that subcooling, and this water glycol coming in the summertime is roughly 60 or 65 degrees.
I think we ran transcritical for maybe half a day, and it was because the gas cooler was 100% plugged with cottonwood, and it was about as low as you could get running transcritical. And then as soon as it got cleaned, it was instantly back subcritical.
Yep.
So I have a question. You said before something about you were having a little bit of a hard time producing because the geo wells aren't heating up, aren't as hot as whatever. Is there anything that you could do as far as on the suction side, as far as floating some of the suction pressures a little bit higher, whether it be on the low temp or the medium temp, in order to get a little bit more capacity?
You potentially could do that, but the problem is like I mentioned, we do have an evaporator, a glycol. So if we need to, in order to get more heat, we got to produce more load. We got to get more compressors running, right? So if I can't dump more load into this glycol loop, then I can't produce any refrigeration effect, and I got no compressor. So if I were to float that up, then essentially I'm reducing the load on the glycol side. So it wouldn't help. What we did a little bit is we actually reduced the suction pressure set point, made the compressors run a little bit harder. We reduced the set point on the glycol loop, and it did give us a little bit more heat output.
Oh, this is making a lot more sense now that I'm actually seeing it. All right, so you have your hot glycol. So you're trying to heat the potable water first, then you're heating up the glycol for the heating loop. And then the next thing is any residual that you have, you're just dumping into that heat exchanger that goes into the basically the thermal wells that are in the ground, correct?
Yeah. We don't actually, the refrigeration is not connected to the wells at all. So the only connection, so we have a loop, which is circulating through the wells, and that warm glycol will dump back into this chilled water loop.
Okay.
So that's the connection. It's not shown on the schematic, but external to the rack schematic is the system schematic. Mm-hmm. And we do have a buffer tank installed on site. So think of it this way, is we've got this chilled water loop. During the winter time, the chilled water coils there's no load on them. They're actually in heating mode and not cooling mode. So this would satisfy set points, which is 75-80% of the load on the compressors. All my medium temp compressors would just shut off.
Gotcha.
So that ground loop, then what it does is we've got a recirculating pump, circulates the glycol through the ground loop and then dumps that warm water back into this loop. So it's artificially placing a load on this evaporator, and then that'll increase the load on compressors and run and give us some THR capability.
Gotcha. So you have, I see two flash gas bypassers. Is just one redundant, or do you need that for capacity's sake?
In this situation, we did need this for capacity, and it does give you a bit of redundancy, but these valves, the Copeland valves from a capacity standpoint, one valve was just a little bit too small for the capacity of the unit.
Okay.
It was enough for the high pressure, but the flash gas, it did need two in parallel.
Okay. Because I know sometimes they're starting to do on the bigger industrial systems, they're starting to have a little bit more redundancy as far as valves. Yes, you might need to put another one in there as far as size. But what I've seen is they'll do redundant valves, HPV and BGV, because those are the heart of the system. Without both of those, you're going to be dead in the water if one of those were to fail.
Yeah.
Gotcha. Anything that you found out that you, as far as operational wise, as far as the CTR valves that we should probably know about?
So I think one of the things from a heating perspective, a lot of the control and sequence of operations, whether it be Danfoss, whether it be Copeland, the first stage of operation to boost heat reclaim is basically just to raise the set point pressure of the high pressure expansion valve. And albeit it does increase, but it doesn't necessarily produce a large gain in the heat output capacity. So basically all you're doing is you're not adding additional refrigeration load. All you're doing is essentially raising the discharge pressure if you do nothing with the fans. Because if you think of it in terms of this way, if the fan set point's the same, let's say you're running a 60-degree drop leg, okay? So you got 60-degree liquid. Now you raise the set points, you still got 60-degree liquid coming in. So your enthalpy difference in your receiver doesn't really change. So your refrigeration effect doesn't change, your flash stress doesn't change a whole lot. What it does do is just add additional heat of compression of just motor heat. So it does improve and it does increase the discharge temperature, but where you get a much and before I move on, one of the negative sides of that, you do have to be a little bit careful with that because the receiver size is really critical. If you've got your drop leg coming down at 60 degrees and now you boost this high pressure expansion valve to say 1200, what you normally operate in subcritical would be a 3-degree subcooling right here. Now you're producing, 3 degrees plus, you've added 400 pounds to the operation of this valve. It's easily to get 30 or 40 degrees of superheat subcooling right here. So
go ahead, sorry.
The downside of that is it does make the rack run efficient, but you got to have enough volume in the receiver then to flood and fill the condenser or the gas cooler.
So it's still running those temperatures, even though it's still, you said 1,200 pounds, when you boost it up in the heat reclaim, and you're still getting that drop leg temperature down to 60. You're still a supercritical fluid, right? So you're still basically not a liquid. We can't technically call it a liquid at that point, even though it's really super cold. Correct?
That's correct.
What does that do for the density? I'm not an engineer, chemical engineer, mechanical engineer. So I'm curious, what that actually does for the density. Does a supercritical fluid more dense? Does it take a larger capacity when you have that, at those states of that refrigerant?
Yeah, it is liquid. So the density from a liquid perspective is going to be more constant as compared to if you increase the pressure for a vapor, but the density still does increase if you're running 733 pounds with 60-degree liquid compared to a 60-degree liquid with 1,200 psi.
So I'm sorry, you say the density would increase at that higher pressure or no?
It does. Yes, it does increase.
Okay. Does that mean you would need to figure in for getting those in what it's running? Basically, would it have to be sized for that worst case scenario, or does it have to be, is the worst case scenario when it's really subcooled at 800 pounds or 600 pounds?
So when you said is it sized for, what are you referring to, Brett?
The pipe sizes are typically based off of capacity, right? So if you have 1,200 pounds and 60-degree line temperature versus 800 pounds, and that basically that same temperature. Is it going to require more surface area inside in order to get that same amount of refrigerant through, just with the properties of the refrigerant at that point, or no?
Yeah, I think I know where you're going with this, and that is a bit unique with trench critical systems. So this drop leg, typically we look at it and people have questioned, why is a drop leg size so large compared to the inlet size? Typically on an HFC system, we're used to seeing the drop leg, liquid side be a lot smaller than the vapor inlet side. And that is entirely based off of the density of that liquid, or whether it's transcritical, whether it's liquid or supercritical in this state. The density is so high that it may even be a supercritical state, but the density is very comparable to a liquid. So if you were to size that pipe size based off of a liquid, which we're used to doing, the erosion effects of that copper would be greatly increased.
Okay. You saw where I was going with that. I was just I'm thinking it through, like what's going to happen when we have, because I when Kevin said that, I had to repeat it like 3 times, and I'm like, repeat that one more time. And he's like, the pressure was this, and the droplet temperature was 60, and all of a sudden I'm getting the computer out, doing the enthalpy diagram. Shit, it's still literally considered a supercritical fluid, but
yeah,
never heard of a supercritical fluid being able to be cooled that temperature.
Yeah. One thing we did on this rack to improve the heat recovery is combination of things. One, you can increase the set point of this, which typical control algorithms do. But secondarily, what they'll do is, if you're still not getting enough heat, then you increase the gas cooler outlet temperature. And that does 2 things. One, your discharge pressure still rises, but you're also now increasing the temperature going into your high pressure expansion valve. So that increases and changes the enthalpy, which then increases the flash gas. So you're artificially just adding artificial load to the compressor. So by raising that, you're not only raising the discharge, but increasing flash gas. So you can get more heat out of it, because you're wasting refrigeration load basically only on the flash gas bypass.
You're basically adding more load to the medium temp compressors, which essentially is adding more heat of compression energy for more heat reclaim, right?
That's correct.
Okay. Cool. Do you want to get right into, do you want to use this one as what we were talking about with the gas cooler bypass, and talk about what Zero Zone's done with that?
Yeah. So I can use this for an example. I think if I could advise, if we can get away without a gas cooler bypass, that's definitely the best. I think the best way to control the discharge pressure in cold ambience is fan control. Now, I know we can't always do that, but if we have enough turn down ratio, and if we have stable control of the fans, then the best scenario is to only use the fan control for head pressure control. If we start to have to get into other things, it does add complexities. It does add additional control loops. So it is more challenging. It is more complex. But there are certain circumstances where, if we are faced with very light loads and we get some very cold ambience and perhaps even some cross prevailing winds that even turning the fans completely off, we're still going to see dropping or decreasing drop leg temperatures, and which can ultimately lead to the rack crashing. You have no choice but either to do one of 2 things. You can either split the condenser or the gas cooler, or you can add the 3-way bypass valve. But from the perspective of which one's better, my experience, both are successful and both can do a good job. But both can be very finicky in their own ways as far as making sure that they control properly and they keep the rack stable. The most important thing is, I've seen situations when it gets cold out and the fans are running at 0 speed and maybe cycling off from 0 to 5% or whatever the current setup is. Even that is not enough, and the temperatures start dropping. Eventually, your receiver pressure starts dropping. And then you eventually lose your medium temp, and the rack just cascades and just falls down. But in that situation, it does not happen quickly. It can take an hour from the onset of things. Ambient temperatures don't change that fast. So as the temperature drops, it may take 30 to 60 minutes from running perfectly fine until it basically falls over. So my point being is, the most successful setup of fan control and or this 3-way bypass is to go very slow. Do not make it aggressive. If this valve opens up too fast and starts dumping hot gas, that just causes a chain reaction. You'll up the line. The high pressure expansion valve will see an increase in input temperature, and then the subcooling, because it's running subcritical and controlling your subcooling, will adjust, and then you get a lot of erratic behavior. That temperature will increase, the valve will close, and then you start to see that the cycling of the high pressure expansion valve, the fans, there's all sorts of bad things that happen. When this valve starts to open, it should take minutes, if not 10 minutes, to go from 0 to 10 or 15% until you start seeing a noticeable effect.
Since you brought it up, because you talked about rack crashing, so Kevin and I had a discussion last week about control as far as the gas cooler fans, and we're both on the same page. If Kevin, you want to explain, or you want me to?
So I like to control the gas cooler. Me and Adam have talked about this before. I like to control the gas cooler fans off of saturation, pressure, it converted to temperature, and run the fans off saturation. I feel that they're more stable off saturation, and most of the controllers do a better job of controlling off of saturation versus temp. It seems like drop leg temp, they seem to hunt more, because when you get a fan kick on, you get that instant drop and drop leg temp, and then you get this hunting going on. Whereas pressure, you get a little bit more of a buffer with that. Saturation doesn't drop as fast.
Kevin and Brett, I've recently been doing some testing very specifically this, and I've seen very positive results by controlling on pressure rather than temperature, and for good reasons, right? You got, from a pressure standpoint, it's immediately reactive. So if a fan increases or decreases in speed or cycles on or off, that pressure is instantaneously affected. The drop leg temperature, on the other hand, is not, right? Assuming that it's located in the rack or close to the gas cooler outlet temperature, there's going to be a thermal lag there. You've got piping conductive resistance for the temperature to actually see. And so there's the response time on temperature is much slower than pressure. But I think the bigger difference is when you start to look at a PID loop and you start to look at the band that you can control with. For example, if we look at just a proportional band, or what Copeland would consider the throttling range, for temperature, 100 degrees, throttling range 70 to 100 degrees provides a pretty slow response. On pressure, if you look at the way pressure behaves, a throttling response of 300 does really well, but it's just a matter of what that offset is. If you're controlling head pressure, the response time for pressure compared to temperature is much faster, and it's much more controllable than it is on temperature. So preliminary results, Kevin, but what I'm seeing is very impressive to control on pressure rather than temperature.
Yeah, we've had really good results with it. And then the other part of it is, we did it on this rack, is the gas cooler fans are all split up. It seems like a lot of the OEMs or the gas coolers are just sending out, everything's wired for 1 AO or in no cycling. That seems to be a huge issue with all the gas coolers, is not having the ability to kill an ECM motor without starting 6 motors at the same time. I understand everybody's trying to build this and get the bid in, but like that seems to be a huge gas cooler issue, is the ability to not be able to cycle fans.
It is like Gudner, they have something inside their control, depending on how many fans. If it's a large system, you have the possibility to turn down the fans and then turn them off. But a lot of people don't enable the LMCC control, and that will actually start cycling fans off when you get to 10% and or below. And it makes a huge difference. And I've just been doing tests where I limit the RPM to 0. And I know you don't want to do that, but even that little bit from 10 to 0%, if you run it, you can basically straight line the gas cooler control. If you don't, then the fans will turn on and off, and you'll get a saw blade effect that you see. And albeit it's horrible, but if the tuning of the fans is still, if it's too aggressive, then things can get out of control quickly.
Yeah, I've never seen the LLCM mode work, but it's always been a thing of, if you don't have a stable control signal, then it doesn't function properly.
Today's episode is sponsored by the Refrigeration RDP Series differential pressure monitors from Westermeyer Industries, now available for transcritical CO2 systems in addition to other common pressures and refrigerants. When the filter element of your coalescing oil separator is contaminated, it can hurt your system's performance and efficiency. But how do you know when it's time to replace that filter? Wait too long to replace, and you could end up with a nasty filter blowout. But replacing too often can be a waste of time and money. The answer is installing a differential pressure monitor. The RDP series differential pressure monitors, including the new transcritical CO2 model, are available now from Westermeyer Industries. To find out more information, email sales@westermeyerin.com. That's WESTERMEYERIN.com.
It's hard to get a stable control signal in the middle of winter.
Yeah, we talked about this where if you're doing the TD control off of temperature, because of the fan cycling, because you're bringing on all the fans all at the same time, you're dropping that temperature really low. So then your temperature goes down, your fan shut off. Then rapidly your pressure built up. And because your temperature is still down there, your subcooling increases from like 0 all the way up to 20 degrees. Then the HPV is, oh shit, and then just opens up and then destroys the subcooling, and then it just goes back and forth. So what happens is, if you look at the graph versus that teeter-totter effect that we were talking about, the LMCC never has a chance. It never even has a fighting chance because it will never run, because it's supposed to run, I think, under 10 or 11% for 5 minutes. And they never get that chance because of how they're doing the TD control. And so essentially you have two PID loops basically fighting each other. You got the gas cooler outlet being controlled for the TD control, but then you also have the HPV, which is using it for subcooling, but can never get a straight. It's like trying to do superheat while you're trying to do an EPR where it's not controlling pressure. It's just off of the temperature. So you never get a constant superheat, so you never get a constant flow. It's the same principle. You basically have two PID loops basically fighting each other using the same thing, trying to calculate off that gas cooler outlet temperature sensor. I'm so glad you said that. I'm so glad you have really good positive results with that. Thank you. You made my night.
I'm not done with it. I have to work out the rest of the algorithm, but I do see a huge opportunity to improve the controllability across the board. You do have to work out at what point to stop controlling off pressure and release back. And I have some ideas, because eventually, as the ambient warms up, you can still float that set point in pressure units, right? You can still walk it up just as you do with a floating TD. It works fine, but you're going to have to think, and we're going to have to work out how we transition into the transcritical zone. Do we switch back to temperature, or do we just keep the pressure set point low enough below the transition point?
That's what we were doing.
I was going to say, you could do the TD of the gas cooler, right? Essentially, if the gas cooler has a 6 degree TD on there, once it hits 80 degrees, it's going to try to maintain 86 degrees, which is right under transcritical. So after that, you really want the fans running 100% anyway.
Exactly.
And so it doesn't really matter at that point. What does it matter if the fans are running 100%? At that point, it's just a de-superheater. And then have some sort of lower pressure as far as the fast recovery, in case you have some kind of drastic load automatically pop up.
Now, Adam, have you guys done much work with splitting condensers, gas coolers?
A little bit. There's several. We have several units out, and the biggest challenge that I have with that is just implementing to go in, cut and cut out, because it creates a very large upset in the system, and it often doesn't recover from it. If you split the gas cooler, essentially now you just double the mass flow through the constant one. That's going to immediately affect your drop leg, and the high pressure valve responds immediately and closes. The pressure increases. You go off on fast recovery, so all the fans start. You unsplit, and then you get this cycling effect. So if you're going to do it, you have to do it in a fashion where you're pretty low in ambient and you're pretty lightly loaded on those gas cooler fans. So when you do one split, it's not such an upset. If you do it 40 degrees, that's too high. If you do it colder at 0 degrees, or basically at the very bottom, you can ride through it, but it's challenging.
So are you guys using CTR valves, or are you guys using automated ball valves to do it?
Ball valves.
So is it like a float? Would it be better to float the opening, like where it's slowly opening, slowly closing, so it's not forcing if it was a floating actuator, so it wouldn't hit so hard, it wouldn't just be on off?
Quite possibly, but I think where the challenges we have is, and I think that goes back to pressure control, which might be very advantageous to get the good quality and stable control using temperature. All your PID loops on the fan control have to be really slow. The challenge with that is, what do you do in the summertime? You start to rack up and you start it up, and now the fan response, the integral is so wound up that you just get no response, and you end up going fast recovery several cycles until things start to smooth out. The same thing happens when you go into split. So if you split and your fans don't recover quickly enough, then you can run in that same situation. But I understand your question, Kevin, in terms of, if you got a slow actuating ball valve, you slowly work itself into it. And I haven't picked up on that. I haven't noticed that. Typically, the ball valves are pretty slow. They might be 90 seconds or 180 stroke rate. So it's a pretty slow transition to begin with.
It's interesting. Yeah, it seems like split would be really advantageous on fixing this, but I think fan control, like you said, is more of the there's more to gain off fixing the gas cooler fans and splitting them up.
Yeah, I would like to say that splitting the condenser would be advantageous, and it should be in theory. It's just a matter of getting the control where, when that upset does occur, that the system can recover or doesn't go back and forth several times.
Are you guys pumping the split side out when you do that? Or okay.
Yep.
How are you accomplishing the pump out with a high pressure expansion valve?
No, just a very small orifice solenoid valve.
Okay.
Where are you going with the pump out? Are you going to the flash tank?
No, it'll go. I think it depends on the orientation. Typically, if you go to the flash tank, that's good enough, right? Because you're getting the majority of all the liquid and everything out of there. Mm-hmm. If it's a larger industrial system, we're pulling it out slow. We can dump it into the low side of the system, in front of a large accumulator. So a little bit of liquid's not going to affect anything or hurt anything.
And what's your thoughts on hot gas defrost?
Typical supermarket system, it's slow. You don't have a lot of the temperature difference to work with it. So it's challenging to move stuff, because let me frame that in terms of the setup. Whether you take it off the low side of the system or the medium temp side, I prefer taking it off the medium temp side and dropping the pressure, because then you can do hot gas with the medium temp and low temp circuits. It doesn't matter. But in a typical reverse cycle, you're dumping that back into the receiver. And if that receiver is running essentially 34 or 41 degrees, typical saturation temperatures, that is your defrost temperature. So essentially, when you defrost, you're really not condensing. You don't have a very large temperature difference. Your coil defrosts at 32 degrees. So you want your defrost temperature to be much greater than 32 degrees so you can condense. So you can put a regulator upstream of the receiver to increase the defrost pressure / temperature, and you can defrost much faster. But with supermarket systems limited to 650 psi, you just don't get that capability to raise that pressure up too much without the risk of a valve hanging up a little bit or blowing the CO2 charge because you build up the pressure too much in the receiver. Industrial systems that are built for 90 bar and you can raise that pressure and temperature, it works very well. You can push and you can in and out, very similar to a typical HFC system, where you can, complete entire defrost in 10 to 15 minutes with drip time, everything. So you might be an active defrost for 5 to 8 minutes and you defrost a coil. So it works very effectively.
When you guys design that, Adam, are you guys doing reverse flow, like through the suction out through a bypass line, or are you doing like Corno does, where they have the oversized valve and shove it through directly through the liquid line back out the suction?
We don't do that. Typically, we divert and then come back down a discrete header.
Okay. Does that or go back up to the inlet of the gas cooler to get recondensed?
It dumps into the receiver.
Okay.
So then that available liquid is used by the circuits, and any flash gas then is just handled by flash gas bypass.
Gotcha. And because you're condensing it, you're getting a little bit of cooler liquid coming out of that return. So you're not adding that much load to the flash tank then, correct?
No, I mean, there are times when you can add a little bit more load to it, because depending on the time of the defrost cycle, at first you're going to get a lot of liquid coming out because you just the coil's cold, it's going to condense very well. But once you start getting closer and you melted all the ice and the coil temperature starts coming up, the last few minutes of the defrost cycle before you terminate is going to be largely vapor. So that vapor dumps in the receiver, and then that turns into flash gas that the bypass has to handle.
So you'll have to excuse me because I'm trying to envision this. So you guys are doing straight industrial systems that are 90 bar, where you're just basically dumping hot gas into the suction of the coil and letting it go back to a discrete header, right? Do you guys have a lower pressure, almost like a cool gas, where you're getting that vapor off the flash tank, or does Zero Zone not do that typically?
We do not do that. And just one correction, we'll never take direct hot gas into the coils. The supply side will utilize basically hot gas or defrost regulator. Mm-hmm. And that can open and close. It's typically a stepper valve that opens and closes. So not only can we control the pressure, we can control the rate of change. When we go into defrost, we might just open that up very slowly and let the pressure build slowly over time, not to shock the coil. Mm-hmm. And then on the return side, we have what we would call a discrete regulator. And that in itself gives its capability to raise or drop that defrost temperature, which is typically, it's going to always be above the receiver because you need a pressure differential to move it. Mm-hmm. But having those two valves give us the freedom to make a lot of adjustments to fine tune the defrost time and cycle.
Does that system has to be the 90 bar in order to accomplish that, or is that something that you found that you can do with a lower pressure system?
You can do it with a lower pressure, but it just doesn't work as well because, like I said, it's 65 to 650 degrees. It doesn't get very high from a defrost temperature perspective, where, with 90 bar system, you can raise that up to a 55 degree saturated temperature, which would be above 650. So to get the full benefit out of it, you really need a 90 bar system.
Gotcha.
And the coils have to be rated for 90 bar. So for a supermarket perspective, they're not there yet. So they're only 650. So you're really limited to defrosting at 525 psi-ish.
And you're basically barely above freezing at that point, because 36 degrees is about 520. So you're not much greater than that. Or you're not really getting that much heat out of it, right?
Yep.
I was going to ask something else. Go ahead, Kev.
No, I was saying anything else you want to talk about?
So I'm trying to figure out. There was something that I had it and then I lost it again.
I guess one thing that to circle back on the fans and the whole sequence, I think to sit down and think about the set points. There's a lot of set points, and those set points matter of how effective the system is going to operate. For example, you've got your gas cooler fans, minimum set point, let's call it 60 degrees. So the fans are going to regulate to no lower than 60 degrees. Then at some point, the fans shut off. They're going to run at a minimum speed. The temperature is still going to drop. Then they'll shut off. So you get a little bit of cycling. And then what happens next? Then now you have the high pressure valve, but that pressure continues to drop even if the fan's off. Then the high pressure valve then starts to regulate to maintain a minimum discharge pressure. And then lastly, if the temperature still, what's going to happen then is think of a typical pressure system back in the days where you have a flooded condenser control. You've got the inlet pressure regulator valve, which maintains a minimum pressure. But as soon as that starts to close, you start to back up refrigerants in your condenser, and then you need a bypass to maintain your receiver pressure. The same thing happens here with CO2, but just with electronic valves. So the high pressure valve starts to maintain your minimum discharge pressure, starts to back up liquid. That liquid temperature coming out of the gas cooler is going to start to drop pretty quickly. That's when your bypass valve comes into play. So when you set these systems up, look at the sequences and make sure that the sub points between one control point and another is enough where you're not competing and struggling. Give each their own little space. For example, the gas cooler set point set for 60, the fan shut off at 55, the high pressure valve regulates at 50, and then maybe the bypass is at 45. So you got a 5-degree kind of dead band in between there to prevent kind of competition on the control loops, if that makes sense.
I see a lot of on startup. I see a lot of conflicting set points between the HPV minimum and the fans. You see them overlapping each other, and then you see this massive hunting. It seems to be a lot of settings, a lot of untuned racks out there.
Yeah,
that's why I like. So some manufacturers are extremely proprietary on how they're supposed to be. I like the fact that you guys literally give a cut sheet with every single rack, which shows you the sequence of operation and how everything's supposed to be. You guys give the set point for the iPro controller, the set points for the VFD. So there's no guesswork. You're not trying to keep it a secret, because you guys probably have the mentality where if the technician doesn't know how it's supposed to be programmed, how they're supposed to be able to fix it. So the fact that you guys are giving all that Front Street, and you guys probably make sure that the fans aren't overlapping with the low pressure set point. Kevin, we talked about this before. It's comparable to having the fan cycling and a holdback valve going on at the same time. Oh, I remember what it was. So we were talking about split for a second. And if you were to, I know, Adam, you said you were concerned about when you put the unit back into operation, you might get a fluctuation.
Yeah.
So if you were to use almost some sort of bipolar stepper to essentially pressurize it, like Walmart with their HFC racks, right before it would come out of split, you would essentially repressurize the split side of the condenser in order to just raise it up, so there wasn't so much like thermal shock, so it wouldn't just really go erratic. Because we all know with CO2, one little change over here affects and it ripples down the line. So being able to take a little bit of that gas and essentially just pressurizing the split to the gas and able to control that.
Yeah, it's important. What I was referring to as far as our goal is to slow down the fan reaction, right? That is key to complete system stability. If you got fans erratic, then high pressure valve, flash gas valve is going to be erratic. Your receiver pressure is bad. You're feeding your expansion valves with poor liquid quality and varying pressures, and it just ripples right through the whole system. If you lock your fans in tight with tight control, that certainly helps give the opportunity to the downstream control devices to do their job. With that being said, is fan control is really critical, and our aim is to keep the response time nice and slow. And it's almost better to maybe vary off a set point a little bit and just keep fan speed more constant. If your set point is 60 and you're floating up and down lazily between 58 and 63, who cares really? But if the fan's now is chasing that 1 or 2 degrees really tight, then you can lose control. My point being is systems have very slow fan control. The problem is if you shut it off in the summertime, you turn it back on and the fans don't respond right away. So the way to overcome that is just startup settings. You got to build a little control logic in there to say, hey, if the rack starts up, push the fans automatically, manually override them, push them to 50 or 75% or whatever for one minute, let things stabilize, cool down, and then release the PID. So that helps a lot.
I wonder if it'll ever get to a point where they're going to do dual set points like you do for a case controller with the dual set points, because people ask me that we've had conversations about why the United States has such a problem a lot of times with the ambient thing and CO2, where my thought is, okay, up in Canada, we have 2 different temperature bands. In the United States, we have several, right? And so they all react a little bit differently, and a rack that works down in Texas is going to be different than a rack working up in Chicago. So like you said, you want that PNID to be fast enough to be in the summertime when it needs to come on and react quickly, it can. but then in the wintertime, you want it slow enough to get a more precise control. So maybe the answer is some sort of dual set point where you have an ambient swing where it's going to control it one way when it's one temperature versus another. Or, like you stated before, maybe just a lower fast recovery set point.
Yep. I think these CO2 racks are very controls heavy. Of course, we all know that. And the controls manufacturers know that as well. And I think over time, the controllability will continue to improve to be able to do some of that stuff.
Anything else you want to talk about, Adam?
I was just about to say that.
Not in particular, nothing that comes on my mind, but I'm still, if you've got further questions or any other topics.
It should be good. I really appreciate you coming on, Adam. It's a really good conversation.
Yep. I think the only other thing, just to respond to you, Brett, you had mentioned as far as the information sharing, I think it's really important because I think OEMs can build a rack, and the success of that really depends on the folks in the field, the refrigeration contractors and the service guys. And if they're not taught, they're not given the information to make them successful, then it's really bad on the rack OEM. It's bad on, the industry, I think, as a whole, from a CO2 bad name. I think we all have a lot still to learn, and we're learning every single day. And just to be able to share information and bring everyone up to speed, I think is really important for the industry.
I agree.
Same here. Adam, I appreciate you coming on. Thank you so much for the conversation, man. It's been really awesome. Hopefully we can do this again sometime. And sorry about hey, we're going to do it tonight. No, we're going to do it tomorrow night. Sorry about that. I'm up in New Jersey.
Yeah, no worries. We made it happen.
So I appreciate you coming on, and we'll talk to you guys later.
All right. Take care, guys.
Here.